Professor Aliou Diop from the University of Saint Louis.
Thank you, Valeria and Sophie, for this initiative. Okay. Here I will talk about statistics of extremes and the random censoring. This is my plan. First, to give some introduction and estimate what we call the conditional extreme value index with censoring. And the third part, to estimate what we call conditional extreme quantiles, also when censoring is present, and to give some simulations. Let us recall a little history. On February 1953, yes, a storm has devastated in the Netherlands and destroy many things, right? And then it is qualified to be a major accident. So a committee is set up to understand the phenomena, to study the phenomena, and to propose recommendations. It takes into account many things, many factors, cost of construction, floods, and something else. Okay, but what we want to say here is this is an accident. This is a rare event with very high impact. And if we look at the past, there was an accident like this. Okay, but the problem is how to understand and try to give some prevision about this phenomenon. And so this phenomenon is very, very rare. And then we have not sufficient data. And so the classical statistical methods cannot be used in practice. I think Amir Shakami has talking about this. But here, the framework is to estimate what we call the extreme quantiles. Extreme quantiles is quantiles which is very high, when here the probability alpha is very, very, very small. It is a small probability, right? And then in some situations, the variable of interest y is observed with a covariate, and this covariate x could be in Rp or in a space with high dimensional, like Sophie said in her talk. Okay, and then x is a variable of interest, y is a variable of interest, and x is an explanatory variable. So it is a kind of regression. Okay, and then what we want to do is to study the extreme of y depending on the observation of x. And we can give some examples in the literature. For example, the magnitude of earthquakes given their location, the location should be the my covariate, amount of production given available inputs. When we want to try to deal with rainfalls given the geographic location, or to analyze survival patients with HIV given their age. And so the focus here is the conditional extreme value index, okay? Extreme value theory. And so the difficulty is we cannot use the empirical distribution function, as Shokami said in his talk, okay? And if we cannot use extreme value index as the empirical distribution function, we have to find an adaptation or a new method to estimate the quantile of this my variable y. Okay, And in this talk, I mainly use, let me go further. In this talk, I can say that we have many domains of applications. For example, in environmental situations where the sea levels is rising up, wind speeds, okay, which has some impact if the wind speeds exceeds a record sometimes, pollution concentrations, etc. And in the finance and insurance situations, we have many applications. It is a growing area of application of extreme value theory. Okay, but let us recall this result, which is the asymptotic distribution of the sample maximum, as Amir present in his talk. It is slightly analog to, or similar to, the central limit theorem, because in the central limit theorem, the objective is to try to understand the mean or the average, but here the problem is to see how behaves the maximum of observation in the univariate case. But this depends on a parameter. This parameter, what I called here in my talk, gamma, it is what we call the extreme value index. This extreme value index is very important. Its signs gives the behavior of the tail, right? When it is positive, the tail is heavy or fat. When it is 0, the tail is very light. I gave here in each situation some examples. And now, when gamma is negative, it is in the variable domain of attraction. As examples, we can recall uniform and beta. Okay, and this is a graphics, some curves, 3 curves, indicating the behavior of the distribution depending on the value or the sign of gamma. And it is very crucial, the knowledge of gamma to estimate extreme quantiles. If you don't know gamma, it is difficult to estimate extreme quantiles. Okay, and now in my talk, if I have 3 domains, we have 3 domains of attraction: the Fresher domain of attraction, Gumbel domain of attraction, and variable domain of attraction. But here, my focus here in this talk is when gamma is positive. When gamma is positive, we can characterize the function f, which is in the domain of attraction of Fresher, by using what we call a regular varying function. And we can say that when the tail becomes heavier, with increasing value of gamma. When gamma is high, the tail is heavy. Okay, and we can give some examples. Now, here I assume that I observed y, which is my variable of interest, x, which is the covariate. Here I suppose that it is in this set R power p with PDF j. Okay, so the objective is to estimate what we call the extreme value index. But this extreme value index should depend on the realization of x, right? So gamma y is a function, and the objective is to estimate this function. Okay, here I gave some reference from the literature. Okay, now the framework is F bar, this is the survival function, could be written like this: y power -1 over gamma. And this gamma is important to estimate. But what we observed a couple. Okay, we observed a couple. Yi is my variable of interest, xi is my covariate. And so using this covariate, I have to estimate gamma y of x. Okay, in the univariate case, we can recall a popular estimator. The popular estimator is Hill estimator. Here I gave the way, the manner how Hill estimator is constructed in the literature. It depends of this result. Okay, y over t, what we call an excess. Yes, a relative excess beyond y, such that y greater than t. And using these equalities, these equivalence, we can build what we call Hill estimator. Okay, but this is how Hill estimator is built, right? But now, what I want is to use exactly this formula, and to adapt this formula to my situation. My situation is I have to observe y with covariate, and observe y with covariate, but in present of censoring. And I will come back to censoring in next step. The estimate used in the literature proposed by Gerber and Al in 1940, it is this kind. If you look at carefully this, here we have a kernel, right? And the kernel which give that we have to estimate around the value of x here, okay, when x is very, very close. And here we can check here that we have Tn, okay? Tn is a threshold, okay? But here in this situation, we use a non-random threshold, okay? H, as in non-parametric statistics, is a bandwidth, okay, which have to choose in order to estimate gamma hat, okay? These authors gave the behavior of this estimator under regularity conditions, okay? But no estimator of extreme quantiles were provided, okay? So we have now to try to see when we have sensory data. Why sensory data? Because it is a situation where the data are incomplete. Okay, let's check here. In the situation, for example, when we are interested of lifetime data, when some subjects are followed in a study, okay, here they enter in the study, and what is interesting for me is what I call the event. Okay, the event could be the death of the patient. Okay, this is the end of the study. Okay, and then this, for this C and A, the event is observed, right? But for D, this one and this one, after the study, for example, the patient died after, and so the length or the duration or the lifetime of B is not completely observed. In this situation, D, the subject left the study, And so we cannot know if it is dead or not. Okay. And so the objective is to apply extreme value here, but with incomplete observation, like missing data. Okay, this is what we did here. And what we can say, we observed this triplet. Xi is my cover rate, delta I is an indicator function using Ci. Ci is the sensor variable, sensoring random variable, and Zi is what is really observed. Okay, so we don't observe the Y. We don't observe the Y, but we want to estimate gamma Y. This is the difficulty of this topic. Okay, what we observed is Zi and Xi, and so delta I is the indicator function. Then the objective is to estimate gamma Y, and gamma Y is not observed. And we can estimate also Q, I say QY here, because it is the quantile function associated to this gamma Y, but from this sample dn. Okay, and now this is the problem. It is, I think, well posed. The conditional distribution function of these my variable are given J, H, and in the Fresher domain of attraction, and we can conclude that gamma Z is this expression, and it is gamma Y times P of X. Okay, what is P of X? P of X is this formula. And then if I want to estimate gamma Y, I have to estimate gamma Z. It is easy to do it because Z is fully observed, and P of X should be estimated also. Okay, and then from this formula, I can build a new estimator. Okay, but let us recall that in the literature, we have some reference from Einmal, Gomez, and Worms. They use this kind of estimator, but the idea is to correct for censoring the classical estimator, okay, by dividing what we call the inverse probability of censoring. Okay, we use here this idea, but to divide by this probability, we have also to estimate this probability, P of X. It is a proportion. It is a proportion of it is the proportion of non-censored observation. Okay, and it is estimated here by using this formula. Okay, and then the final estimate I get is gamma hat. I put H here because it comes from the Hill estimator, and gamma hat is calculated using Z. Z is fully observed. P hat is the proportion of non-censored observation. And by dividing this estimator by this one, we can get a new estimator. And this one is what we call gamma hat C as censored estimator. Okay. And then to tackle the asymptotic properties of this estimator, we can have some regularity condition, like Lipschitz condition on gamma, on J. J is the density of Y, and on the logarithm of L. L is a slowly varying function. Okay, and this is what we did, and we estimate first the P hat, and we gave its asymptotic normality in this first situation, but using some technical conditions, which is really to check in when we have some examples, and we estimate gamma hat, gamma y by gamma hat ch, and we give also its behavior. But we can notice that the asymptotic variance we get here, we can say that it generalize the situation where there is no censoring it is absent of censoring, okay? And the objective of this asymptotic normality is to build interval of confidence, okay? Interval of confidence for gamma y. Let us recall that y is not observed, okay? And now the next step is to estimate the extreme quantiles, but conditional extreme quantiles, but it depends of x, okay? But when alpha is fixed, this can be this estimate can be given by I say by classical estimate, right? It is difficult when alpha n goes to 0, okay? When alpha n goes to 0, we cannot merely use the classical condition, but we have to extrapolate. It is what we did here. Extrapolate and to use what we call the kernel Weismann estimator. This is the kernel estimator we build, but it depends on Q hat beta of n. This is the estimator inside the data. This is the estimate outside the data, because the extreme quantiles, usually it is difficult to do it if you have to estimate outside the data, because outside the data you have maybe no data or not enough data, okay? So this is an extrapolating term which appear here, okay? And then this estimator is built and its asymptotic normality is given, okay? Now let us give some example of simulation, okay? Here y is now x is my coverage, delta, it is an indicator function indicating that my data is, my observation is censored or not. Zi is what is really observed. And using different size, sample size with a Pareto distribution, because I assume that in this work, I use only Fresher distribution. And here I use gamma y, okay? This function which is already used in the literature by Girard and its co-author. And my objective here is try to see if my methods functions well using gamma y, okay? But we have to know what is the proportion of sensory data. We try to work with 10%, 25%, and 40%. Objective is to estimate gamma y and q, okay? And since the method is a non-parametric method using kernel function, to use this kernel. But if you change the kernel, the result is not not affected, okay? And we have comparison with what we call the completed case. The completed case is the case where slightly we ignore what is censoring. And now what is important here is the choose of H and the choose of Tn. H, I said it is a bandwidth. Okay, we use a cross-validation method. Okay, and Tn, it is a threshold. But in this talk, we suppose that this threshold is not random. Okay, so we consider Tn like Z, and K, and we select K as follows. Okay, how to select Ks? We calculate gamma hat, okay, for successive blocks. For example, we try to divide the data into blocks of length 15, for example. And each block, we calculate gamma hat, and we try to pick up the value of K, which minimize the standard deviation. Okay, the block with minimal standard deviation, and we take the median of K, which I call here K star. And finally, this is what we did, and we calculate gamma hat, and this is the final result. And to have a view of what is did here, if you look at this curve is the curve I want to estimate. These are box plot, okay, and we use the censoring, the percentage of, or the proportion of censoring 10%, okay, in the left here, in the middle 25%, and the right 40%, okay, and we check that when the proportion of the censoring percentage is growing, the estimate is more and more is not good. I mean, okay, it's not very good. It is good here, but what I mean is it is better when the proportion is small, right? And this is the simulation of the extreme value index, okay? And when we change the sample size, we have this result. And now the last step is to estimate the conditional extreme quantiles, okay, using exactly the same methodology, okay? And this curve is a curve of the true curve, okay? We try to estimate it using some points here and to try to build the box plot. And we are really happy when we look at this result, depending on the proportion of censoring, 10%, 25%, and 40%. Okay, thank you. This is what I wanted to share with you, and you can find here some reference. Merci beaucoup.
Thanks a lot, Aliou. Is there any question from people sitting in this room or comments?
Yes, thank you for the talk. But what is the connection with the quantile regression in general and your method?
What is
the relationship with quantile regression?
Okay. Yes, because in quantile regression, usually we work on the average. On the average or on the mean. What I want to say is, if we don't tackle the extreme value of the regression, okay, we use the classical method. Or when you want to tackle the regression using the extreme value situation, we have to use these techniques, okay? The quantile regression is not very far from this. The difference is the quantile regression is not extreme, but here the situation is a situation where the probability to exceed some high quantile is very, 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 very small.
Okay, thank you.